In the last lecture, I showed that for weak and slow-moving sources, the space-space components of the metric perturbation in Lorentz gauge are given by h bar ij. The bar denotes the trace-reversed metric perturbation, and it's a function of the spatial coordinates x and the time coordinate t. This is equal to 2 divided by r times the second time derivative of ij of t minus r, where r is just the distance from the coordinate origin to the field point x. We're assuming that the coordinate origin is buried deep inside the source. And ij is the second moment of the mass distribution. So it's a function of time, and it's given by the integral d3x of t00 of x and t, xi, xj. So this is the second moment of the mass distribution. The reduced quadrupole moment of the source is defined from the second moment by removing the trace, and we denote that as iij with the bar through the I. The metric perturbation in the transverse traceless gauge is obtained from h bar ij using a projection operator. Pij equals delta ij minus k hat I k hat j, where k hat is the unit wave vector, so it's a unit vector that points in the direction of propagation of the gravitational wave. So here's our source, and the xyz coordinates with origin deep inside the source. This is the field point x, very far away from the source. And here are the gravitational waves propagating past the field point. And this is the wave vector k. So you can see that because the field point is far away from the source, the unit wave vector is in the radial direction. In other words, it's equal to x vector over the magnitude of x vector, which is r. And a common notation for a unit vector in the radial direction is n hat. So with this notation, we'll write the projection operator as Pij equals delta ij minus ni nj. The metric perturbation in TT gauge is defined by Hij TT equals Pik Pjl minus 1/2 Pij Pkl times h bar kl. This is the metric perturbation in Lorentz gauge. Now, using our result for h bar in terms of the second moment of the mass distribution, we have 2 over r times the second time derivative, and I'll use dots to denote the second time derivative. So that's I dot dot kl, and it's a function of t minus r. Now let's define the transverse traceless part of the second moment of the mass distribution as this operator acting on I. So this is Pik Pjl minus 1/2 Pij Pkl acting on I, KL. Then our result for the metric perturbation in TT gauge becomes Hij TT, which of course is a function of the field point and time, equals 2 over R times the second time derivative of the TT part of the second moment of the mass distribution as a function of the retarded time T minus R. Now it's a fairly simple exercise to show the following. The TT part of the reduced quadrupole moment, which is just PIK PJL minus 1/2 PIJ PKL acting on the reduced quadrupole moment. This is equal to the TT part of the second moment of the mass distribution. As a result, we can replace I with I bar in our expression for the transverse traceless metric perturbation. So the result is Hij TT of x and t equals 2 over R times the second time derivative of the reduced quadrupole moment, the TT part, evaluated at the retarded time T minus R. This is our main result, connecting the source motion to the gravitational waves that they produce. And this result holds for any weak, slow motion source. In particular, it holds for what I called in the previous lecture case number 1 sources that have negligible internal gravity, and it also holds for what I called case number 2 sources that have non-negligible internal gravity. This result can also be used for case number 3 sources, which are strong but slow moving. But in this case, the reduced quadrupole moment can't be determined from an integral over the source. It has to be determined from the gravitational field in the weak field region outside the source. And not from an integral over the mass distribution of the source. Now recall the results from 2 lectures ago. That would be lecture number 33 in this series. There we showed that the stress energy momentum tensor for gravitational waves is given by T mu nu equals 1 over 32 pi times partial mu Hij tt partial nu Hij tt, where the angle brackets denote an average over several wavelengths or several wave periods. In particular, the energy density in gravitational waves is T00 equals 1 over 32 pi times the average of Hij tt dot from the time derivative times Hij tt dot. And now if we use our result for HTT in terms of the reduced quadrupole moment, we have 1 over 8 pi times r squared times the average of I bar ij tt triple dot times I bar ij tt triple dot. And let's remember the right-hand side is evaluated at the retarded time, t minus r. Now let's use our general result to write down the energy flux in the radial direction. The energy flux is also the momentum density. That's T0K. That's the energy flux, and to pick out the radial direction, we take the dot product with the unit normal in the radial direction. This is 1 over 32 pi times the average of hij dot tt times partial k hij tt times nk. Now let's carry out a side calculation for this factor. This is partial k hij tt, and using our result for htt, we have partial k acting on 2 over r times I bar double dot ij tt, and that's a function of t minus r. Now partial k is a derivative with respect to xk, and xk appears in two places as the magnitude of xk, namely r right here and again here. So first, taking the derivative with respect to the 1 over r here, we have minus 2xk over r cubed times I bar double dot ij tt, and that's a function of t minus r. And differentiating with respect to the xk here, we have minus 2xk over r squared times I bar triple dot ij tt as a function of t minus r. Now, because the field point is very far away from the source, this term with 1 over r cubed is negligibly small compared to this term with 1 over r squared. So in the large r limit, this is approximately minus 2 times, I'll write xk over r squared as nk over r, times I triple dot ij tt as a function of t minus r. Now using this result in here, you'll notice that the nk times nk just gives a factor of 1. We find for the energy flux in the radial direction, T0k nk equals minus 1 over 8 pi r squared times the average of I triple dot ij tt times I triple dot ij tt. This is evaluated at the retarded time. By the way, notice that apart from the minus sign, this is just the same result that we had for the energy density. So T0k nk is just minus T00 for gravitational waves. From the energy flux, we can compute the rate at which the source loses energy through gravitational radiation. This is the gravitational wave luminosity. This is defined as an integral over the energy flux through a sphere at large radius and the area element of the sphere is r squared d omega. Using our result for the energy flux, this is minus 1 over 8 pi times the integral over a sphere at large radius of d omega times the average of I bar triple dot ij tt, I bar triple dot ijtt evaluated at the retarded time. For the remainder of this lecture, I plan to work through in detail the calculation of gravitational waves from a binary star system. Consisting of stars M1 and M2 in circular orbits about one another. We'll assume these are ordinary stars, so gravity is weak and their motion is slow. We'll also use the result for the gravitational wave luminosity to estimate the rate of energy loss, which determines the rate of inspiral of the two stars. Let the orbital plane be the xy plane. With the origin at the center of mass of the two stars. We'll use L to denote the separation between the two stars. R1 is the radius of M1's orbit. And R2 is the radius of M2's orbit. Of course, L is just equal to R1 plus R2. We'll also use the common notation mu to refer to the reduced mass. We can determine the orbital frequency of the system by setting the Newtonian gravitational force, that's m1 m2 over L squared, times Newton's constant, which we set equal to 1. We set this equal to the mass times the centripetal acceleration. So for the mass m1, we have m1 times the centripetal acceleration is r1 omega squared. And this, of course, simplifies to r1 omega squared equals m2 divided by L squared. We can carry out the same calculation for star number 2. We have m2 r2 here. What we find is r2 omega squared equals m1 over L squared. Now add these two equations. We find r1 plus r2 times omega squared equals m1 plus m2 over L squared. Since r1 plus r2 is equal to L, this tells us that L cubed times omega squared is equal to the total mass m1 plus m2. This is, of course, Kepler's third law of planetary motion. Now let's multiply this result by m1 times r1. We have m1 r1 times L cubed omega squared equals m1 r1 times m1 plus m2. Now m1 times r1 times omega squared we can replace with m1 m2 over L squared. And this gives L cubed times m1 m2 over L squared equals m1 r1 times the total mass. Now solving for r1, we find r1 is equal to the reduced mass mu divided by m1 times L. And by similar calculation, we find r2 is equal to the reduced mass over m2 times L. Now our goal is to compute the gravitational waves from the binary star system. That is, we want to compute the metric perturbation in TT gauge, which is given by 2 divided by r times the second time derivative of the reduced quadrupole moment, the transverse traceless projection, evaluated at the retarded time. For this, we need the second moment of the mass distribution, ij, at time t equals integral d3x of t00 of t and x times xi xj. Because our source is non-relativistic, the motion is slow and the stresses are very small. The energy density is dominated by the rest mass density. So this is approximately rho naught, which I'll use to denote the rest mass density. Now the rest mass density at location x and time t can be written in terms of Dirac delta functions as m1 times delta of x minus r1 cosine omega t times delta y minus r1 sine omega t times delta z plus m2 times delta x plus r2 cosine omega t delta y plus r2 times sine omega t times delta z. It's now straightforward to calculate the components of the second moment of the mass distribution. For example, let's look at I11 or Ixx. That's equal to the integral d3x of rho 0 times x squared. From this first term in rho naught, we have m1 times the integrals over y and z just give a factor of 1, and the integral over x gives r1 cosine omega t quantity squared. And now for the m2 term, we have m2 times r2 cosine omega t squared. So this simplifies to m1 r1 squared plus m2 r2 squared times cosine squared of omega t. And now this coefficient can be simplified using the results we derived earlier. This is m1 times r1 is mu over m1 times L plus m2 times r2, which is mu over m2 times L. And this equals mu squared times L squared times 1 over m1 plus 1 over m2. You can easily check that this quantity in parentheses is just the inverse of the reduced mass. So this is equal to mu times L squared. Then our result for I11 is mu L squared times cosine squared of omega t. The remaining components of I can be computed very easily as well. The results are I22 equals mu L squared times sine of omega t, that's sine squared of omega t. I12 is equal to mu L squared times cosine omega t times sine of omega t, and all of the other components vanish. I13 equals I23 equals I33 equals 0. So this is the second moment of the mass distribution. We obtain the reduced quadrupole moment by removing the trace. So the trace of IKK, is I11 plus I22 plus I33. That's just equal to mu L squared. And the reduced quadrupole moment, I bar, is defined by I minus 1/3 delta ij times the trace. So for our binary star system, I bar 1 equals mu L squared times cosine squared of omega t minus 1/3. I bar 2 is equal to mu L squared times sine squared omega t minus 1/3. I bar 3 equals minus 1/3 mu L squared. I bar 1 equals mu L squared times cosine omega t times sine omega t, and the remaining components vanish. I bar 1 3 and I bar 2 3. This is the reduced quadrupole moment. Our next task is to construct the transverse traceless part of I bar. This is done using the projection operator Pij equals delta ij minus ni nj, and the definition of the TT part is Pik Pjl minus 1/2 Pij Pkl times I bar Kl. And by the way, since the TT part of I bar and the TT part of I are the same, we could skip the step of computing I bar and simply use I, the second moment of the mass distribution, instead of I bar. Now recall that n is the unit vector that points in the direction of the observation point, or the field point. So here is our coordinate system, x, y, and z. Our two masses, m1 and m2, are orbiting about one another in the xy plane. And here is our observation point, x, y, z. The unit vector n points in this direction. And we can specify this direction using spherical coordinates. So this is the polar angle theta, and this is the azimuthal angle phi. Then the xyz coordinate components of the unit vector n are just sine theta, cosine phi, sine theta, sine phi, and cosine theta. Now in principle, the calculation of the TT components of I bar is straightforward. However, it's very tedious and very messy. Let me give you the result of just one component, the 1,1 or XX component. So I bar 1,1 TT is equal to mu times L squared over 64 times cosine of 2 omega t minus 2 phi times the quantity minus 5 plus 4 times cosine of 2 theta plus cosine of 4 theta plus 19 plus 12 cosine of 2 theta plus cosine of 4 theta times cosine of 2 phi minus 16 times the sine of 2 omega t minus 2 phi times 1 plus cosine of 2 theta times sine of 2 phi. And in addition, there are t-independent terms. And the reason I don't bother writing the t-independent terms is because the metric perturbation depends on time derivatives of I bar tt, so these terms won't contribute. Now we could go ahead and compute the other components of I bar tt in this Cartesian coordinate basis. This is the xx component. We could compute the yy and zz components and so forth. But notice that these components are not really what we want. If we're sitting here at this observation point at angle theta and phi, what we would really like to know is the components of I bar tt in a basis that's adapted to the direction of propagation. So let's construct a set of basis vectors at this point. One of the basis vectors is the unit normal n, which I'll redraw here. Another basis vector is in the direction of increasing theta. We'll call that e sub theta. And the third basis vector is in the direction of increasing phi. We'll call that vector e sub phi. Of course, e theta and e phi are orthogonal to n, so they're transverse to the direction of propagation of the gravitational waves. Now, it's not too difficult to show that the Cartesian coordinate components of these two basis vectors are given explicitly by E theta is equal to cosine theta, cosine phi, cosine theta, sine phi, and minus sine theta. And for E phi, we have minus sine phi, cosine phi, and 0. So these are the x, y, z, or 1, 2, 3 components of these basis vectors. And now we compute the components of I bar tt in this basis. For example, the theta-theta component of I bar tt is just I bar ij tt times ei theta ej theta. And writing I bar tt in terms of our projection operators, we have ei theta ej theta times pik pjl minus 1/2 pij pkl times I bar kl. Remember, E theta is orthogonal to n, so that tells us that E theta I pij is just E theta j. In other words, when p acts on a vector in the transverse direction, it's just the identity operator. So I bar tt theta theta becomes, from this first term, E theta k, E theta l, I bar kl, and from the second term we have minus 1/2. E theta dotted with E theta just gives a factor of 1, and we're left with p kl I bar kl. Now remember, pkl is delta kl minus nk nl, but because I bar is trace-free, then delta kl times I bar kl vanishes, and this reduces to E theta k, E theta l plus 1/2 nk nl acting on I bar kl. A similar calculation gives I bar tt phi phi equals E phi k E phi l plus 1/2 nk nl times I bar kl. And the off-diagonal component is I bar tt theta phi. That's equal to E theta k E phi l I bar kl. Of course, we can also compute the component of I bar tt in the direction of propagation. Let's call that I bar tt in n. And just like this definition, that's equal to I bar tt ij times ni nj. But because of the projection operators, this just gives 0. And likewise, I bar tt in theta and I bar tt in phi vanish. So only the transverse projections of I bar tt are non-zero, and in this basis, consisting of n, E theta, and E phi, these are the theta theta, phi phi, and theta phi components. And now, using our previous results for the reduced quadrupole moment, I bar, it's straightforward to calculate these tt projections. And these are much easier to compute than the components in the Cartesian coordinate basis. The results are I bar tt theta theta equals minus I bar tt phi phi equals mu L squared divided by 4 times 1 plus cosine squared theta times cosine of 2 omega t minus 2 phi minus sine squared theta. And I bar tt theta phi equals mu L squared over 2 times cosine theta times sine of 2 omega t minus 2 phi. Now the metric perturbation is constructed from the second time derivatives of the tt projection of the reduced quadrupole moment. So let's compute I bar tt theta theta double dot, and that's just minus I bar tt phi phi double dot. Each time we take a time derivative, we pull out a factor of 2 omega. So this is equal to, and a minus sign, this is minus mu L squared omega squared times 1 plus cosine squared theta times cosine of 2 omega t minus 2 phi. Now, mu is the reduced mass, which is m1 times m2 divided by the total mass m1 plus m2. And recall from before we derived Kepler's third law, which says omega squared is equal to the total mass divided by the cube of the separation. So these factors together give us m1, m2 divided by L. So our result here can be written as minus m1, m2 over L times 1 plus cosine squared theta times cosine 2 omega t minus 2 phi. And the corresponding result for the second time derivative of I bar tt theta phi is minus 2 times m1 m2 over L times cosine of theta times sine of 2 omega t minus 2 phi. And now we're finally ready to write down the metric perturbations in TT gauge. Recall they're given by HTT ij at the observation point x at time t is equal to 2 over r is the distance from the source to the observation point, times the second time derivative of the tt projection of the reduced quadrupole moment, and that's evaluated at the retarded time. So taking the theta-theta projection of this equation and using our result here, we find that HTT theta-theta at time t and location x, and that's just equal to minus HTT phi phi at t and x, is equal to minus 2 m1 m2 over r times L times 1 plus cosine squared theta times cosine of 2 omega times t minus r minus 2 phi. Similarly, we have HTT theta phi of t and x equals minus 4 m1 m2 over r times L times cosine theta times sine of 2 omega t minus r minus 2 phi. Now these results just define the plus and cross polarizations of the gravitational wave. So a binary system consisting of masses m1 and m2 in circular orbit about one another emits gravitational waves with both plus and cross polarizations. The relative strength of these two polarizations depends on the observation angle theta. Note that the waves are strongest along the z-axis where theta equals 0 and pi. These are the directions perpendicular to the orbital plane. The wave emission is weakest in the orbital plane where theta equals pi over 2. In fact, the cross polarization vanishes in the orbital plane. Also note that the frequency of the gravitational waves is twice the orbital frequency of the two stars. Now let's compute the energy emitted in gravitational waves by the binary system. Earlier in this lecture, I derived the energy flux as T0k nk equals minus 1 over 8 pi r squared times the average of I bar tt triple dot ij, I bar tt triple dot ij. Now the energy flux in a positive sense is actually given by the stress energy momentum tensor with upper indices 0 and k. So let me raise these indices, and raising the 0 index flips this sign, so this becomes a plus. So this is now the energy flux in the positive end direction, that is in the radial direction. And by the way, this should be evaluated at the retarded time t minus r. Now we can carry out the contraction over these indices I and j using the basis e theta, e phi, and n. So this becomes t0k nk equals 1 over 8 pi r squared times the average of I bar tt triple dot theta theta squared plus I bar tt triple dot phi phi squared plus 2 times I bar tt triple dot theta phi squared. Now because the phi phi component of I bar tt is just minus the theta theta component, these two terms are actually the same, and we can write this result as 1 over 4 pi r squared times the average of I bar tt triple dot theta theta squared plus I bar tt triple dot theta phi squared. Now we previously wrote down the second time derivatives of I bar tt theta theta and theta phi components. They're right here. So we just need to take another time derivative of these results. And that gives I bar tt theta theta triple dot equals 2 omega m1 m2 divided by L times 1 plus cosine squared theta times sine of 2 omega t minus 2 phi. And I bar tt triple dot theta phi is equal to minus 4 omega m1 m2 over L times cosine theta times cosine 2 omega t minus 2 phi. And now we can square these results and add them together to obtain I bar tt triple dot theta theta squared plus I bar tt triple dot theta phi squared equals 4 omega squared m1 squared m2 squared divided by L squared times 1 plus cosine squared theta squared times sine squared of 2 omega t minus 2 phi plus 4 times cosine squared theta times cosine squared of 2 omega t minus 2 phi. Now we need to average this result over several wave periods. So the average of sine squared of 2 omega t minus 2 phi over several wave periods is 1/2. And likewise, the average of cosine squared of 2 omega t minus 2 phi over several wave periods is 1/2. So when we average this quantity, we have a factor of 1/2 coming from both the sine squared and the cosine squared. And this gives the following. The average of I bar tt triple dot theta theta squared plus I bar tt triple dot theta phi squared is equal to 2 omega squared m1 squared m2 squared divided by L squared times, from here we have 1 plus 2 cosine squared, but the 2 cosine squared combines with the 4 cosine squared to give 6 cosine squared theta, and then we also have from here cosine to the 4th theta. And now we can write down the energy flux. It's T0K nk equals 1 over 4 pi r squared times this quantity, evaluated at the retarded time, But notice there's no time dependence in this result, so the evaluation at the retarded time doesn't matter. Let's also recall from Kepler's third law that omega squared is equal to the total mass divided by L cubed. And let's denote the total mass as capital M. So our result is T0K Nk is equal to 2 over 4 is 1 over 2 pi r squared times, from these factors we have capital M, the total mass, times m1 squared, m2 squared, divided by L to the 5th power, times 1 plus 6 cosine theta squared plus cosine to the 4th theta. As you can see, the energy flux depends on the polar angle theta. It's strongest at theta equals 0 and pi. Those are the directions perpendicular to the orbital plane. Now let's compute the luminosity. That's the energy per unit time emitted by the binary system as gravitational waves. Luminosity is obtained by integrating the energy flux over a sphere at large radius. So using our result for the energy flux, we have luminosity is equal to the integral of d omega, that's d theta d phi times sine theta, times 1 over 2 pi. The r squared here cancels the 1 over r squared here. We have capital M times m1 squared, m2 squared, divided by L to the 5th power, times 1 plus 6 cosine squared theta plus cosine to the 4th theta. The integral over phi gives a factor of 2 pi, and the integral over theta is straightforward. The result is 32 over 5 times the total mass, capital M, times m1 squared, m2 squared, divided by L to the 5th power. Although we assume the binary system consists of stars in circular orbits, the loss of energy through gravitational radiation will cause the orbits to decay and the stars will spiral together. The decay is very slow for weak, slow-moving sources, so our approximation of circular orbits is reasonable. Let's use our result for the gravitational wave luminosity to estimate the rate of orbital decay. First, we need the energy of the system. This can be estimated as the sum of the kinetic plus potential energies. So the kinetic energy for mass number 1 is 1/2 m1 times its speed, r1 omega squared. For the second mass, we have 1/2 m2 times r2 omega quantity squared. And for the potential energy, the interaction energy between the two masses, we have minus m1 m2 over the orbital separation L. Now, using once again our result from Kepler's third law that omega squared is equal to the total mass divided by L cubed, and also remembering that R1 plus R2 is just the total orbital separation L, it's easy to show that the total energy is just minus 1/2 m1 m2 over L. And now let's set the rate of change of the energy of the system equal to the rate at which gravitational wave energy is produced. That's minus the gravitational wave luminosity. In other words, d by dt of minus 1/2 m1 m2 over L equals minus 32 over 5 times total mass m1 squared m2 squared divided by L to the 5th. And this simplifies to L dot, the rate of change of the orbital separation, equals minus 64 over 5 times capital M m1 m2 over L cubed. This result can also be written in terms of the orbital period. Let's let tau denote the orbital period. So this is 2 pi divided by omega. And remember, omega squared is the total mass divided by L cubed. So this is m over L cubed to the minus 1/2 power. And this is the orbital period for the system. Now differentiating tau with respect to time and using this result for L dot, we find tau dot over tau equals minus 96 over 5 times total mass times m1, m2 divided by L to the 4th power. Now let's have a bit of fun by putting some numbers into these formulas. For example, we can consider the pulsar, PSR 1913 plus 16. This pulsar was discovered in 1974 by Russell Hulse and Robert Taylor. It's in close binary orbit with another star, so the system is commonly referred to as the Hulse-Taylor binary. The masses of the two stars in this system are roughly equal. They're both approximately 1.4 solar masses. And the orbital period is about 8 hours. Now the orbits of the stars are not circular, they're elliptical. So the separation between the stars varies between about 1.5 times the radius of the Sun and about 5 times the radius of the Sun. So our analysis of the gravitational radiation for binaries and circular orbit doesn't really apply here, but we can go ahead and use some of these numbers to get a rough order of magnitude type estimate of the effects of the gravitational waves on the Hulse-Taylor binary system. Our formula for the rate of change of the orbital period, including the factors of Newton's constant and the speed of light, is minus 96 over 5 times g cubed over c to the 5th power times total mass times m1 times m2 divided by L to the 4th power times tau. In evaluating this expression, we need to choose a value for the orbital separation L. I'm going to choose the value at the lower end of this range because we expect the strongest distortions in space-time and the strongest gravitational wave emission to occur at the closest separation. So choosing L equal 1.5 times the radius of the Sun, our prediction for tau dot is minus 2.5 times 10 to the minus 12 seconds per second. In other words, for each second that passes, the orbital period decreases by about 2.5 times 10 to the minus 12 seconds. And this is roughly on the order of 1/10 of a millisecond per year. Now the actual value of tau dot as obtained both from observations and from a more careful calculation that takes into account the eccentricity of the orbits, is minus 2.4 times 10 to the minus 12 seconds per second. Note that our result, which assumes circular orbits, is quite close to the actual value, but that's largely due to random luck. Remember, there's a large range of choices that one can make for the value of the orbital separation, and this choice has a significant effect on the outcome of the calculation. In general, the effects of eccentricity are important and should not be ignored. Now let's consider the gravitational wave luminosity for the Hulse-Taylor binary. Inserting the appropriate factors of Newton's constant and the speed of light, the luminosity is 32 over 5 times g to the 4th over c to the 5th power times total mass m1 squared m2 squared divided by L to the 5th. Inserting the numbers, including the value of L at the lower end of the range, this is about 1.8 times 10 to the 25th watts. The actual value is about 7.4 times 10 to the 24th watts. So in this case, our prediction, which assumes circular orbits, is off by a little bit more than a factor of 2. I'll leave you with a couple of questions you can answer for yourself. What is the gravitational wave luminosity of the Earth-Moon system? In other words, how much power is radiated in gravitational waves by the Earth and Moon? Could this be used to power a light bulb? How about the solar system?